Today I'm here to talk about inflection points. This is where there's a change in concavity in a function. When a function goes from concave up to concave down, that point where it changes over is an inflection point. This is going to occur when the value of the second derivative is 0. Here's a graph to demonstrate. You can see that this graph initially is concave up. And then when I reach the point xi, the inflection point, the graph changes over to concave down. We notice that in the beginning, the first derivative, f prime, is increasing, and that f double prime is greater than 0 or positive. At the inflection point and then after, f prime, the first derivative, is decreasing, and f double prime is less than 0. So what happens to f double prime precisely at xi? Well, it's going to have to equal 0 when it switches over from concave up to concave down. Let's find the inflection points of the following function. First, I'm going to find the first derivative by using the shortcut of the power rule. Here you can see f prime, which was obtained by moving the exponents down and multiplying them by the coefficients, and then taking a 1 away from the exponents. Now I'm going to find the second derivative. So using the same shortcut, I get 6x minus 18. I now want to set f prime equal to 0, so I can figure out where those inflection points may be. By setting 6x minus 18 equal to 0, I add 18 divided by 6, 18 6, which equals 3. That is the location of my inflection point. And let me graph that. So as you can see here from this graph, I have an inflection point at 3. I have a local max at -2, a local min at +8, and those values were found by determining where the graph was increasing and decreasing, utilizing some different things with the first derivative. Let me go ahead and find the values of the local max and local min, and then also find the y value of the inflection point. And I'll simply do this by evaluating the function at -2, 3, and 8. And here are the values that I came up with for my inflection point, my local max, and my local min by simply plugging in 3, 2, and 8 into my original function f of x. Now you can see I've adjusted my y scale here a little bit just to get this graph to appear on the screen. I'm most interested in the inflection point located here at 3, -146. That's where the graph is changing over from concave down to concave up. If I were to evaluate the value of the second derivative, f double prime, to the left of 3, I would see that it would be negative. If I were to evaluate the value of f double prime to the right of 3, I would see it would be positive. And if I have a sign change in the second derivative, in this case going from negative to positive, I will have an inflection point. Take a second and sketch the following graph that fits all of the following conditions. If you want to hit pause to go ahead and do that, now would be a great time. And here comes your answer. On the first bullet, I have critical points at critical point at x equals -3. That tells me that the value of the derivative is 0. And I did my best to try to illustrate that in the picture. On the second bullet, f double prime is 0 at x equals 2. That tells me I have an inflection point. jumping down to the next to last bullet, if f double prime is less than 0 to the right of 2, that tells me my graph is starting to go concave down. F double prime is greater than 0 to the left, that tells me that's concave up. So the graph is changing from concave up until it hits my inflection point into concave down. The third bullet, f prime is less than 0 to the left, that indicates that the function is decreasing. And as you can see, the function is coming downhill. The fourth bullet, f prime, the first derivative, is greater than 0 to the right, tells me that the function is increasing. So everywhere after -3, the function has to be going uphill. So I have to have a decreasing function, then it turns into an increasing function with a concavity change at 2, going from concave up to concave down. Here's an interesting note in a similar fashion when we talked about f prime. So just because f double prime equals 0, that doesn't actually always mean it is indeed an inflection point. You do have to check the sign before and after when the f double prime equals 0, and I mean the sign of the second derivative. You have to look for a sign change from positive to negative. Just like when you had f prime equals 0, that doesn't mean that there's going to be a local max or min. There has to be a sign change in f prime to be a max or a min. Using derivative, let's find critical points and inflection points of the following function. First, I'm going to have to find the first derivative, f prime. To do that, I'm going to be using the product rule. Here's the first step using the product rule. You can see I have a chain rule when I took the derivative of e to the negative x. The derivative of negative x is -1. Plus, take the derivative of x is 1, and then leave the second function. This I can rewrite. So I've multiplied the x times the -1, and there's no need to put the additional 1 in front of the e to the negative x. And now I'm going to factor out a 1 minus x. So I pulled the negative x off of the front of e to the negative x, and the 1, so I could write this as 1 minus x, all that times e to the negative x. And now I want to know, when is the first derivative 0 or undefined? That's going to give me my critical points. E to the negative x will never be 0 or undefined. However, the value of 1 minus x, if that entire quantity were the value of 0, and then I multiply that times e to the negative x, then the entire expression would be equal to 0. Well, what's going to make 1 minus x equal to 0? Well, I can set that equal to 1, and you'll see that if x equals 1, that's going to be the value that determines a critical point. Now let's find the second derivative and determine when it equals 0 or it's undefined. So I leave the first function alone, 1 minus x. Take the derivative of e to the negative x, is e to the negative x times the chain rule of -1, plus take the derivative of the first function, the derivative of 1 minus x is -1, and leave the second function alone. Now you can take it, leave it, take it, or you can go in the other order, because when we're adding here, everything is the same. And I want to simplify this expression in green as well. So I'm going to distribute the -1 to the parentheses. Instead of 1 plus minus 1e to the negative x, I'm just going to make that -1e to the negative x. And in similar fashion as before, I'm going to pull out the -1 plus x and the -1 in this expression, simplifying it even further. So now you have the second derivative in parentheses x minus 2 multiplied by e to the negative x. And I want to know when that equals 0 or is undefined. Well, the only time that that expression will equal 0 is if e to the negative x equals 0. That never happens. Or if what's in parentheses equals 0, so that when I multiply it times e to the negative x, the entire expression would equal 0. Well, you can set x minus 2 equal to 0, and you'll get when x equals 2, you have the second derivative being equal to 0, thus telling me I have a possible inflection point. So I want to go a little bit further here. I want to know what exactly is happening at this x equals 1 from setting the first derivative equal to 0, and what exactly is happening when x equals 2 setting the second derivative equal to 0. Are these maxes, mins, inflection points? What's going on here? Well, to do that, I'm going to use sign charts. I'm going to evaluate first the first derivative to the left of 1 and to the right of 1 and see if there's any sign changes. In creating my sign chart, let's evaluate f prime anywhere to the left of 1. An easy option would be to find the f prime of 0. And when I do that, I will get a positive number. Let's evaluate it to the right of 1 using the f prime of 2. When I do that, I'm going to get a negative number. So exactly at 1, if I'm going from positive to negative, I now know that I have a max at 1. Well, now let's see what's happening at a value of 2 when I set the second derivative equal to 0. So let's pick a test point and find the second derivative to the left of 2. I'll plug in the value of 1, f double prime of 1. When I do that, I'm going to get a negative number. Something to the right of 2, I could use f double prime of 3. When I do that, I'm going to get a positive number. And if I'm going from negative to positive, there is indeed a concave change. It's going from concave down to concave up, letting me know that that is an inflection point. So this is also a critical point at x equals 2. Again, I did f double prime of 1, so I did 1 minus 2 times e to the negative 1 to get that negative number. And when I did f double prime of 3, I did 3 minus 2 times e to the negative 3 to get a positive number. So here we have a max at 1, an inflection point at 2, and if I wanted to know the actual values for y, I could evaluate f of 1 and f of 2 in my x times e to the negative x. And that pretty much wraps up some things with inflection points.